2.1 Functions. Every function is a relation, but not every relation is a function. So how do we figure out when a relation is a function? This is an example of a relation. Let's say you have 2 and 5 as your x's, and 1, 2, and 4 as your y's. Let's say these arrows indicate coordinates. You would have a pair of 2, 1, 2, 2, and 5, 4. This is a relation, however, it is not a function because this x has 2 y's. On the other hand, it would be a function if, say, your x's were 1, 2, and 4, and your y's were 2 and 5. Once again, arrows indicate coordinates. This would be a function because each x only has one corresponding y. Whereas here, this x goes to both 1 and 2, even though x1 and x2 both go to y being 2, it's different because they're two different x's. Two different x's can have the same y, however, the same x cannot have two different y's. Here is a function box. In order for a function box to be functional, say you put in apples. You'll want to know that every single time you'll get blue bananas. If, say, one day you put in apples and you got, licorice. That's some licorice. Then it wouldn't be a function because you wouldn't be able to predict it. Some days you might get blue bananas and some days you might get licorice. You want to know that every single time you put in bananas, you get every single time you put in apples, you get either bananas or licorice, not both. A function is a function if you're able to predict the outcome every single time. Your x's are also called your independent variables. They are the variable that you put into the function, or in this case, function box. Your y's are your dependent variables. They are the variables that come out of the function box. The function box only works if only one kind comes out for every kind of x. Okay, so this is the definition of a function. Let x and y be two non-empty sets, and by non-empty they mean that each set of x and each set of y must have numbers in them. A function from x into y is a relation, because every function is a relation, that associates with each element of x exactly one element of y. So basically what this is saying is that, say you have two sets. So here's your set of x, 1, 2, 3. Here's your set of y, 4, 5, 6. For every x, there's only one element of y that is associated to. 1, 1, 1. Like we saw earlier, each x can only have one y. Sometimes two x's have the same y, like both 1 and 2 might go to 4, but that's different because 1 goes to 4 and 2 goes to 4. 1 doesn't go to 4 and 5. It only matters where the x goes. It's okay if a y technically has two x's. Now, this set of x is also called the domain. And this set of y is also called the range. Domain, x, range, y. Now here are two examples. One is a function and the other is not. So which one is? Let's look at the first one. every single of the domain goes to one of the range except for Burger King chicken sandwich and McDonald's McChicken, who both go to a fat level of 23. However, this one would be considered a function because it's two different x's going to the same y. You don't ever see one x going to two y's. Now let's look at the one below it. This one is not a function because 0.71 carats can be 1,575 or 1,952. This would not be a function because this is the domain, carats is domain, and price is range. One value in the domain goes to two different values in the range. That means that this is not a function. How do we know when an equation is a function? So let's take this one. Y equals 7x minus 14. Y can also be written as f of x. Now let's say we're trying to find f of 3. This means that you're plugging in 3 for every single time there's x in the equation. So it'd be 7 times 3 minus 14, which is 21 minus 14, which is, of course, 7. If we try it with f of 5, 7 times 5 minus 14 equals 35 minus 14, which is 21. Now let's take the equation x squared plus y squared equals 1. This equation is in implicit form, which we'll get to later. So now let's first put it so that we can put it in f of x form. So y squared equals 1 minus x squared. Y equals plus or minus the square root of 1 minus x squared. So, because in this form it's already plus or minus, we know that for values between negative 1 and 1, two values of y will come out. So say we were to plug 0 in. Y equals plus or minus the square root of 1 minus 0 squared. 1 minus 0 squared is, of course, 1. Therefore, y equals plus or minus 1. It can either be negative or positive 1, which means that this equation is not a function. Now, earlier, I mentioned something called f of x, which basically is the value of f, or really the range, at a given x, or the value of the function f when a certain x is given. So now let's say you have something like f of 3. This means that x equals 3. If you had something, say, f of negative x, this means that for every x you would plug in negative x, so on and so forth. Now, let's say you have a function defined as f of x equals 2x squared minus 3x, and you were asked to evaluate it at, let's say, f of x plus f of 3. So first you would start with plugging everything in. We know that f of x is 2x squared minus 3x. And f of 3 would be plugging 3 in for every single time there's an x. So we would still add, put it in parentheses if you want. It will be helpful later on if you have, say, minus instead of plus. Now 2 times 3 squared minus 3 times 3. Close parentheses. Simplify it. 2x squared minus 3x is in the simplest form. Plus 2 times 3 squared is 18 minus 9. 2x squared minus 3x plus 9. And there you go. This function f of x equals 2x squared minus 3, evaluate it at f of x plus f of 3, which turns out to be 2x squared minus 3x plus 9. Now I mentioned implicit form earlier. Basically what it means is that you don't tell it, you don't say something, for example, y equals 3x plus 5. This is an equation in explicit form. And in implicit form, or an equation in implicit form would be like 3x plus y equals 5. Your y isn't isolated, which means that unlike this one, this is implicit. So, implicit and explicit. The only difference between the two is whether the y is isolated.